Hi folks and welcome. I'm Wesley Williams, and today we're going to cover number systems. Now, this should be sort of an introductory lesson for anybody who's going to begin their study in computer science or electronics. And it's really just sort of a math lesson, all right? So we're going to get into basically how computers communicate, process, store, and otherwise use data and make it meaningful. It's the underlying system to all that. So we're going to start off with number systems. Now, as you may or may not be aware, we use a numbering system. We as in humans, we use the decimal numbering system. And so the base 10 numbering system is pretty simple. And in the decimal numbering system, we have, let me go ahead and write this. In the decimal numbering system, we have 10 digits. And these digits are represented as such. We've got a 0, we've got a 1, 2, 3, 4, 5, 6, 7, 8, and 9. Those are the 9 digits that we have, or those are the 10 digits that we have. When you include 0, it becomes 10. So 0 through 9 is your 10 digits, and all numbers, when we use the decimal numbering system, all numbers can be represented using this base 10 system, using these 10 digits. All right, and when we start counting, so we got 0 through 9 here. When we start counting, we reuse the digits, right? Once we run out, once we got 0 through 9, we need to represent 10. We do this by using place values, and so we write down 0 and a 1 to represent the next number. All right, and we got two place values now. We've got what we call the ones place, right? And then we've got the tens place. All right, and that's because this is a base 10 numbering system. When we talk about base 10 numbering systems, we're talking about having different place values, all right, that are all powers of 10. So 10 to the 0 is the ones place, right? There's always anything raised to the 0 is 1. So every numbering system actually has a ones place. Then we have 10 to the 1, which is just 10, right? And then 10 to the 2 would be 100, right? And if we had a 4-digit number, it would be 10 to the 3 for 1,000, just like that. And so if I was representing a number, let's say 3,964, then that would be 3 thousands, 9 100s, right? 6 10s, and 4 1s. That's how we kind of represent those numbers. And so this is a really large number. And then, of course, 10 is the first of our multi-digit numbers. Of course, we know that after 10, we get 11, 12, and 13, and on and on and on. When we count all the way up to 19, right, we reset the 9 back to 0. Reuse a 0, and then increment the 1 here to a 2, right? And then it's 21, 22, so on and so forth, till we get to 29, and then we reset 9 back to 0 and increment the 2 to a 3, right? It becomes 30. And we keep going. You might get 89, 90, 91, all the way up to 99. And then after so we've run out of digits here, the 9 has to reset to 0. This 9 also has to reset to 0. And since we're out of digits, we need a new place value. So we end up with 100. We get the 100s place. All right? And that's kind of what it looks like when we're counting in the decimal numbering system. Now, most everybody's familiar with this method of counting. And this is the numbering system that's used by the world, right? Now, some folks think that it got its start because we have 10 fingers and we can use those 10 fingers for counting purposes. I'm not sure if that's actually true, but this is the numbering system we use, and it is based on 10. Now, you might say, well, why do we need to use any other numbering system? Well, it's mainly because of computers that we consider other numbering systems. Can we make an electronic device that has 10 distinct voltage levels or 10 distinct current levels? Yes, is the short answer. But as with all electronic devices, nothing's really perfect. And if we have these different voltage levels established, any kind of mistake or variance in manufacturing or anything, variance in the environment, could lead to the voltage level that's being produced to not really fall within the correct parameters. And so in other words, you can have machines that are off just because of the environment they're in or just because of the manufacturing of that particular machine. So rather than deal with all the variabilities that would have to be closely monitored in a base 10 digital machine, we use a base 2 system for computers. Basically, we have the presence or absence of a voltage to represent all the numbers in a computer system. So if the voltage is present, that registers as a 1. If the voltage is absent, that registers as a 0. All right? So let me put over here on this side the binary numbering system. I'm going to use a different color. Here we go. This is the binary numbering system. This is base 2. Okay, this is base 2. So we start off with a 0 and a 1, and then we're out of digits. All right, so we only have a 0 and 1 to work with. So we're going to have to use place values a little bit more aggressively in the binary numbering system. So 0 and 1, and then we have to reset this 1 to 0 and add a place value and put a 1 there, and that becomes 1 0, which is actually 2, right? And so 1 0 is 2, and then 1 1 would be the next number, right? And then we're once again out of digits in both place values here. So we have to reset this one, and then add a new place value. And that ends up being the binary number for 4. All right? And then the next one up, we just increment by 1. So we get 101 like that, and then we increment again, which gives us 110. And we increment again, we get 111. All right? But now, once again, we're out of bits. We can't, once we have 1s in all the place values, that's it. We need a new place value to represent the next number. So we reset all of these to 0 and add a new place value, and that ends up being the number 8. And so on and so forth. So we got 1 0 0 1, 1 0 1 0, all right, 1 0 1 1, and let me scroll down a bit. Oops. Sometimes it can be really trying to get it to work right. There we go. I'm going to scroll it down a little bit. Here we go. So that ends up being, let's see, 1 0 1 1. That would be the number 11. All right, and this is 12 in binary. 13. All we're doing is incrementing by 1. 14. And 15. All right, and once we get to 15, which is all 1s, 16 needs an extra bit, a new place value. So you can see the place values need to be utilized a lot. We have new place values for each one. And just like in the decimal numbering system, these place values are based on the numbering system. So this is base 10, and the decimal system is base 10, so everything's a power of 10. In binary, everything is based on the 2's power, right? Everything is power of 2. So that means if I have a binary number like, I don't know, 1 0 1 1 0, then each of these digits is represented by a place value. Or each one of these bits, actually, we call digits. In a binary number system, we call them bits. And so we have, let's see, underline that one, that one, that one, that one, and that one. So we got 5 place values here. And this would be 2 to 0, which is 1. Remember, every numbering system has 1's place, because anything raised to the 0 power is always 1. And then 2 to the 1, which represents the 2's place. 2 to the 2, which represents the 4's place. 2 to the 3, which represents the 8's place. And 2 to the 4, which represents the 16's place. All right? And so that ends up being a binary number. Actually, you can figure out what it is in decimal by just adding up the place values where there's a 1 present. So we got 16 plus 4 and plus 2. That'll be 16 plus 6, which is 22. So this is the number 22 if we were to write it in decimal. But this is the binary representation of the number 22. All right, and that'd be 10110. Now, just as a convention, I would recommend writing any binary numbers, write them with a little subscript of a 2 to remind yourself and to anybody reading your work that this is a binary number and not the number, 10,110, right? You want people to be, you want people to look at numbers and be able to figure out what they are. So 10110, and then a little subscript of a 2 is how I'd write that. All right, and that's the binary numbering system right there, and it's pretty straightforward. You'll notice when we were counting in binary initially here that there's some patterns, right? The ones place alternates between 0 and 1, 0, 1, 0, 1, 0, 1. And the reason for that, this is a base 2 numbering system. The reason for that is because binary numbers that end in 0 are even numbers, and binary numbers that end in 1 are odd numbers. And so it alternates between 0 and 1. Notice the 2's place, which is the second place value here, also alternates, but it alternates every 2. I can, to make it a little bit clearer, I can go ahead and fill these. I can pad some zeros in here if you'd like. And you can kind of see the pattern a little bit more plainly when we pad with zeros. You get the alternating 0, 1, 0, 1, 0, 1 on the ones place. You get alternating 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1 in the 2's place. And you get the alternating 0, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1. You get that alternating pattern on the 4's place. And then obviously on the 8's place, you alternate every 8 zeros and 1s, right? And so that's kind of how it works. And if we went to the 16's place here, we could have 16 zeros and 16 1s in that pattern there. And you can kind of use that to go ahead and draw, a large amount of binary numbers if you need to. You can use that pattern to fill in. If you're counting or something like that, you can use that to fill in each of your binary counts very easily. So use that pattern as you see fit. All right, and this is binary numbers and decimal numbers. Moving on, we may want to know how to convert some binary numbers into decimal numbers and decimal numbers into binary numbers, and so the conversion process requires a little bit of thought. So if I want to convert something, let's go from decimal to binary. This is a pretty straightforward process. If we're converting from decimal to binary, we start with a binary number, or a decimal number rather, and then we convert it. There's actually several methods for converting it, but I'm going to show you the one that I use the most. Anyway, let's go ahead and figure out a decimal number. Let's give ourselves at least a 3-digit decimal number. Let's do, I don't know, 113. All right, so this is the number 113 in decimal, and I want to know what it is in binary. I want to get the binary equivalent of that. Well, what you can do is just go ahead and write out some place values. All right, and we can start from the rightmost spot right here and go to the left and kind of just fill it in with the place values. Remember, the first place value is always 1, right? And then 2 to the 1, which is 2, 2 to the 2, which is 4, 2 to the 3, which is 8, 2 to the 4, which is 16, 2 to the 5, which is 32, and then 2 to the 6, which is 64, and 2 to the 7 would be 128, but 113 is less than 128, so you want to stop at the number right before the next number is too big, right? It's kind of like Price is Right. You want to get up close to the number but not go over it. So 64. 64 is less than 113, but the next number would be 128, which is greater. So we're going to stop at 64. And we're going to place a 1 there. I'm going to use red for this. We're going to place a 1 here. All right, and then what we're going to do is subtract 64 from 113. So you take 113 and subtract 64. All right, and this should be fairly straightforward. Let's see. 13. I think that's 9. And 4. Right, 49. So now we have 49 left over when we subtract 64. And so I'm going to see if 32 is less than 49. It is. So I'm going to subtract a 32 from that and place a 1 in the 32 place value. All right, we're left with 17. 17 is also bigger than 16, which is our next number. So I'm going to put a 1 there and subtract 16. That's going to give us a 1 left over. 8 is bigger than 1, so we put a 0 there. 4 is bigger than 1, so I put a 0 there. 2 is bigger than 1, so I put a 0. And 1 is equal to 1, so I put a 1 there. Subtract that out, and we get 0. All right, and so now this is the binary representation of the number 113. All right, so really all we're doing is we're subtracting out the place values. Starting with the biggest place value, subtract those out. And whenever you get a place value that is bigger than what you have left over, you put a 0 there. All right, and that'll be a good way to convert between decimal into binary. A very simple process right there. We'll do one more for practice. So let's do something a little easier. Let's do 65. All right, 65. So let me go ahead and convert that over to 65, converting it over to binary. And again, we're going to go ahead and create the place values here. Let's see, 64 is a place value that is just below 65, so we'll start with that. Then there's the 32 place, the 16, 8s, 4, 2, and then 1. All right, so now we're ready to go. We can subtract 64, so I'm going to place a 1 there and then subtract it. And notice there's a 1 left over, right? 1 is smaller than 32, 1 is smaller than 16, 1 is smaller than 8, 1 is smaller than 4, and 1 is smaller than 2, but it is not smaller than 1. It's the same size. Put a 1 here. And we're left over with 0. So that'll be the binary representation of 65. So that is much simpler. But you can see how the process works. And that process works rather well. Again, you just want to start with the place value that is the smallest, well, the largest, before going over the decimal number you're trying to convert. So there you go. Pretty straightforward. Let's go the other way, though. All right. So we're going to convert from binary to decimal. And when we convert from binary to decimal, we're going to start, of course, with the binary number. And I'm going to just kind of randomly make one. All right, so here we have a binary number. I don't know what it is off the top of my head. We know it's binary because I used a subscript of 2. And we're going to convert it to decimal. How do we do that? Well, we're going to kind of go in the reverse of the way we did before. We're simply going to underline each of the place values. It's pretty straightforward. So I'm going to start with here. That's the 1's place. Of course, we know that's the 2's. That's the 4's. 8, 16, 32, 64. All right. And what we're going to do is eliminate, or actually not eliminate, what we're going to do is just add up the place values that have 1's. So this is going to be 64, right? And then 16, and then 8, and 1. And so this is going to be 19 when we add up the, let's see, 10, yeah, that's 19. We carry the 1. And this ends up being 89. Okay, so this is 89 base 10. All right. Just add up all those place values. You get 89 when you do that. So that is the binary number for 89. Okay, in base 10. Another binary to decimal conversion. Do another one real quick. All right, so we've got that binary number right there. And I'm going to convert it into decimal. And I'm going to go ahead and put my place values in here. That's the ones place, right? 2, 4, 8, 16, 32, 64, and 128. Now, I know there's a 128 here. There is a 64. 32 and 16 have zeros, but 8 has a 1. 402 has a 1. And 1 has a 0. So any places where there's a 1, you just add up those place values. All right? And so we get 22. 8 plus 4 plus 8 plus 2 is 22. Carry the 2. We get 10, right? 6 plus 2 plus 2 is 10. That's a 0 with a carry. And then 1 plus 1 is 2. So this ends up being 202, base 10. All right? Or you can write it like that, 202, base 10. Okay? I think that makes sense. And if you have any questions, feel free to reach out to me. I hope this is a pretty plain way to do some conversions between binary and decimal. I think this is. Decimal and binary are going to be the primary two numbering systems that we're going to be talking about in this section. But in addition to that, we are going to talk about hexadecimal, but I think that would be best served in a separate video. So stay tuned for part 2 of number systems, and thank you for watching.